With Leibniz's rule, we have a two-variable function, f of xt, and we're taking the integral with respect to x from a of t to b of t. And we'll talk about dt in a second, but what's going on here? This is a function where f is, as we know, dependent on x and t, but x is also dependent on t. T is usually time. So as time moves, x is moving as well as the function f. Our bounds of integration are x values, of course, because this is with respect to x, but as t moves, it moves x, and so we can think of the bounds of integration as little functions of t. And then we're taking the derivative with respect to t of this whole thing, and Leibniz's rule says that that equals the function, or we basically move delta t, d dt inside the derivative. We can take the derivative with respect to t first. So we express that as the partial derivative with respect to t, which is the proper way to do it with a two-variable function. After we take the derivative with respect to t, then we can proceed with the integral with respect to x and go ahead and do our integral. But then we also have to subtract the function evaluated at a, which a is a function of t. Okay, so a of t, nt times dA dt plus the function evaluated at b. And again, b is dependent on t. I maybe should have put a of t and b of t in here. But just remember there are functions of t, and then this times dB dt. And so how is that derived? And so what we're going to do is I'm just going to take this part in the green, and we're just going to start working it. We're going to use first principles. So if I want to take the derivative with respect to t of something, I would just say the limit as delta t approaches 0, and then we're going to set up a difference quotient. So we would be dividing by delta t, and then we would take this function and we would make t a little bigger. And keep in mind, I'm just going to usually put a and b. We're just going to remember they're functions of t, but I'm not going to write a of t and b of t all the time. And so we would have our function a. Well, actually, let me write this first. So if t gets a little bigger, well then a and b are going to be a little bigger. So we could express the bounds of integration as a plus a little more, a plus delta a, and then b plus delta b. And then from that we would subtract the function where we started out. And so basically we've just taken this and we have expressed it with first principles as a derivative with respect to t. Okay, now what we're going to do is we're going to take this integral and we're going to split it into 3 using the bounds of integration. And so what I'm going to do is I'm going to split this thing into 3 of them. We're going to have one going from a to b, one going from a to a plus delta a, and one going from b to b plus delta b. And this one will be subtracted. And if you think about it, these 3, if you have 3 integrals of this function here, with these bounds of integration, they're going to be equal to these. And we can see that easily by, if you think of the x-axis, and we have a, and then if a shifts a little bit because of t, then we see the bounds of integration moving here. And this is the area from here to here. That's what we want. Well, if you think about it, if we go from A to B, Okay, so that takes care of this one. If we go from b to b plus delta b, that gets us up to here. So now we have this whole area. We have too much here. If we subtract from a to delta a, well, then that's gone, and we can see that these three integrals would be equal to the area of this one. Okay, so continuing on here, we're going to take this and express it as all three of these. This one we're going to leave alone. So I'm going to take this, and the first one I'm going to use is this one. So A and B, again, never forgetting that A and B are functions of t. Okay, and then we're just doing this. We're going to do three of these. And I'm gonna put this. So we took care of that one. Now I'm gonna put this one next, because they have the same bounds of integration, and we can turn that into its own difference quotient. Okay, that takes care of that one. Now I'm going to do this one. So now we're back to copying this function. And that takes care of that one. Okay, so this is equal to all of this, which is equal to all of this, and so let's keep going here. So these two they can be expressed as one integral from a to b using linearity of integrals. And so we're just going to have this minus this. And this, of course, should have brackets around it. With this and this, we are going to use two things to turn them into something else equivalent. We're going to use the mean value theorem for integrals and the second fundamental theorem of calculus. So let me get rid of all of this. We'll come back to it later. Okay, so I cleared some space here, and I took this term and I put it over here, and now let me get rid of this, and we're gonna work on transforming this term. First of all, though, let's talk about the second fundamental theorem of calculus. We know that if you have some integral, so I'm just doing an example with a single variable integral here. We know when we take an integral, we can express that as we take the antiderivative at b minus the antiderivative at a, and that is equal to this integral. So we'll end up using that. And then another thing that we also have is the intermediate value theorem for derivatives. So if we have a secant line going through 2 points, let's just call that A and that B, we know that the slope of this is equal to f of also know, according to the intermediate value theorem for derivatives, that there's going to be some point in between here, at least one point, where you could draw a tangent line at such that its slope is equal to, okay, we'll call this C, in between A and B. And if we take the derivative function and evaluate it as C, there's going to be some C in there where the slope is equal to the secant slope. The tangent slope is equal to the secant slope. And so we're just going to move this around. And let me move it up a little. Okay, so I just moved what I was working on up a little bit. Now we're going to make it more useful to our purposes by, let's just take the integral of both sides. And so if I integrate term by term, I'm just going to have big F of B minus big F of A, again using the linearity of integrals. And here, the integral of this would just be F of C okay, and B minus A here would be constant, so we don't need to do anything with them. And so the idea that we're going to use here is when we put them all together, let's just take this thing and move it down here. I'm still just being general. I'm not talking about the function we started with. I'm just showing the principles here that we're going to use. So if I have an integral, I can express it this way, and I can also express it this way. And so that's what we're going to use to transform this. Okay, so taking this, we know that we can express this as big F, so meaning the antiderivative of the upper bound. And since this is, we're back to our two variable function now. Well, since we're doing this with respect to x, t is constant, so we're just copying the t stuff into here. But this integral would be big F of all of this minus big F of just A, and then t is still the same as it was. Okay, so this is also equal to the function little f evaluated at some c in between the lower and upper bounds. So I'm just going to call that c1 because we're also going to do one with b, that the other integral on the far right that we were looking at a little bit ago. So you know the c's are probably not going to be the same, and so we can say that this integral would be equal to the function little f evaluated as c1, and then c is still just along for the ride right now, and then we would have upper bound minus lower bound, but then we've got a minus a, so this really ends up being delta a. Remember, these are constant because they're dependent on t. The t is not moving right now because we are doing the integral with respect to x. So let me just change this back to delta a. And so basically we used the fundamental theorem of calculus and the intermediate value theorem for derivatives to show that we can express this as this. And then by the same logic, we're going to have one with b. Let me just do a different color. If we did the same thing with b, then we would have, we'll call that c2. And then delta b. Okay, we're back to what we were doing. All I did just now was I copied and pasted what we were just doing, the two things we did with the A and delta A term and the B plus delta B term. That's all I've done. I just copied and pasted it here. Let me rewrite them though so they don't look weird. Okay, I just recopied those, and now we're going to turn it into this. What I'm going to do right now is I'm just going to take this 1 over delta t, and let's get rid of it here, and let's put it back. And the only thing left to do now is take the limit as delta t goes to 0. So this first term here, all of that, if we take delta t to 0, well, that's just the derivative with respect to t. And in this case, it would be a partial derivative. So inside the integral, we're going to have the partial with respect to t. Okay, and so this is done now. And of course, these are functions of t. We don't want to forget that. Okay, what happens when delta t goes to 0 here? Well, okay, remember this C1, this was where we used the mean value theorem, and we had a and a plus delta a, and this was some value in between. Okay, but as delta t goes to 0, delta t goes to, did I say that right? As delta t goes to 0, delta a goes to 0 because a depends on t, which means this basically just turns into a, and since C1 has to be in between, well, then the limit of C1 as delta t goes to 0 is just a, and so we're basically just replacing C1 with a. And I'm going to go ahead and put a of t just to remind us that it is dependent on t. As delta t goes to 0, we end up just having t here. And then we still haven't looked at this. Well, if we have a change in a over a change of t, and a depends on t, a is a function of t, well, as they get infinitely small, that just turns into dA dt. And by the exact same logic, we're going to take this, and it's going to end up being the function at b times dB dt. So that's Leibniz's rule. And one last thing, keep in mind that if these had been constants, these two terms wouldn't be necessary. Because if b and a, the bounds of integration did not depend on t, well, dA dt, that would just be a derivative of 0, and these terms would disappear. And so if that was the case, if you had a derivative, if a and b were actually constants, and you were doing this, well, in that case, you don't need these two terms. Basically, you just need this term, and what it amounts to is you're just taking the partial derivative of the function, partial with respect to t, first, and then you take the integral with respect to x. So the red here is Leibniz's rule if a and b are constants.